Over the last century, neuroscience has become incredibly good at mapping the brain's physical machinery. If you want to know exactly how a photon of light hits the retina, travels down the optic nerve, and triggers a physical reaction, we can trace that mechanical pathway perfectly. Philosopher David Chalmers calls these the easy problems of consciousness. They are purely structural. But Chalmers pointed out that even after we map every single synapse, we are left with what he termed the hard problem. The hard problem asks a deceptively simple question. Why does the mechanical firing of neurons inside a pitch-black skull result in the vivid, subjective sensation of being alive? Why does processing a wavelength of light feel like seeing the color red? We could possess a perfect map of the electrical wiring for the entire human brain, and yet analyzing those physical blueprints would never automatically explain the origin of our inner subjective experience. To isolate exactly what this subjective experience is, philosophers use a famous thought experiment, the philosophical zombie. Imagine a hypothetical being that is an exact atom-for-atom physical duplicate of a normal human. This physical duplicate walks, talks, and reacts to pain exactly like you do. But internally, there is absolutely zero subjective experience. The lights are on, but nobody is home. If you can conceptualize a perfectly functioning biological machine that acts human but possesses no inner life, it leads philosophers to a strict logical deduction. Physical facts alone cannot fully account for consciousness. If an organism can theoretically process data and survive entirely in the dark, then our vibrant subjective feeling must be an elusive extra ingredient layered on top of the physical universe. This disconnect is illustrated by another famous thought experiment called Mary's Room. Imagine a brilliant neuroscientist named Mary, who has lived her entire life in a black and white room. Through textbooks, she learns every single physical fact that exists about human color vision. She knows exactly how specific wavelengths bounce off objects and trigger the visual cortex. Then one day, the door opens. Mary steps outside and sees a red apple for the first time. The philosophical dilemma is this: does she learn a new, non-physical fact about the universe in that moment? If she does learn something new, what it actually feels like to see red, then there is a strict boundary between physical knowledge and raw subjective feeling. Philosophers call this the explanatory gap. Some researchers attempt to close this gap by embracing panpsychism, the hypothesis that consciousness is a fundamental, almost magical property woven into all matter, much like mass or electromagnetism. But defining consciousness as an ethereal, non-physical property creates a serious scientific roadblock. As long as we treat the mind as an unmeasurable ghost, the gap between the brain's physical mechanics and our inner lives remains impossible to close. A radical alternative has emerged from philosophers like Keith Frankish and Daniel Dennett. Their approach suggests that the hard problem itself, and the thought experiments used to prove it, might be built on a massive misunderstanding. Dennett suspects that the zombie hunch is an intuition trap. He proposes that if a system functions exactly like us, thinks it is conscious, and claims to have feelings, then there is no extra ingredient to subtract. In this view, we are the zombies we imagine. This is the core of illusionism. It posits that what we call subjective experience does not exist as a magical, non-physical essence. Instead, the feeling is a functional byproduct of how the brain monitors itself. This theory addresses our deepest counterintuition, the raw certainty that we are currently experiencing a mind. Illusionists argue that the brain lacks the resolution to see its own underlying gears, leaving us with a distorted, schematic sense of an internal ghost. Our internal architecture tricks us into believing a second, non-physical reality exists inside the system. This leads us to investigate a mystery that may be nothing more than a blind spot in our own self-monitoring. To understand exactly how this trick functions, look at the graphical interface of an early desktop computer. Computer scientists call this the user illusion. A complex system deliberately hides its underlying code and microscopic transistors behind simple, clickable folders so that a user can actually operate it. Our biology utilizes the exact same design principle. A human brain contains 86 billion neurons and trillions of synapses. If the brain had to continuously track and understand every single one of those microscopic chemical reactions, it would be paralyzed by the sheer volume of data. What we perceive as this mystical, ethereal consciousness is simply the brain's simplified schematic interface. It generates a stripped-down model of itself to efficiently navigate its relationship with the surrounding environment. Under this framework, the subjective self is revealed as a basic required piece of functional architecture for any complex system that needs to learn, adapt, and regulate its own behavior. This table outlines the specific parameters required for consciousness under this functional view. By defining consciousness strictly through mechanisms like an introspective loop, an environment model, and integrative capacity, we can map its presence across highly diverse physical systems, entirely independent of human biology. Consider the Physarum polycephalum, or slime mold. It completely lacks a brain or nervous system, yet it utilizes externalized physical slime traces as spatial memory to map its surroundings, solve mazes, and adapt its behavior based on past experiences. A decentralized collective entity, like a flock of birds, monitors its own internal density and cohesion. It acts as a distributed introspective loop, adapting to environmental threats as a single, unified system. By moving the hard problem out of the realm of abstract metaphysics and into the domain of systems theory, scientists are granted a practical metric. Engineers can actively measure these functional loops and even design self-awareness into future artificial intelligence architectures. This adaptive user illusion represents biology's most elegant functional solution, the architecture that enables intelligence to navigate, survive, and thrive across any physical substrate in the universe.